Shashank Sule will present his work on error analysis for the committer solver based on target measure diffusion maps. Target measure diffusion maps is a little bit simpler algorithm than the one featured in the work with Luke Evans. However, it is more amenable for theoretical analysis. Analysis is still pretty complicated. For this reason, we chose to start with a simpler version of this algorithm. The goal of this work was to understand how does the error in computed committer and in computed transition rate depends on the bandwidth parameter epsilon and the number of data points. So please, Shashank, share your screen and start presentation.
All right, hello. My name is Shashank, and I'll be talking about my work on the error analysis of target measure diffusion maps as part of Dr. Cameron's group. Many physical systems that we're interested in often exist in a few number of metastable states and perform rare transitions between them. For example, a molecule may have two stable configurations and transition very infrequently between the two configurations. It turns out that such physical systems can be idealized by a very simple mathematical model known as overdamped Langevin dynamics, where the change in the state X is described by a drift and diffusion term, which is random. This allows us to study our system through an energy landscape where the minima of the potential corresponds to the two metastable states. As you can see in this toy example, the process X spends most of its time in the states A and B with a rare transition between the two. This geometric picture allows us to ask the question of what is the chance that a process started at the point X ends up in B before A. Now, this probability is known as the committer function, and in general, using this definition, it is prohibitively expensive to find the committer. Nonetheless, in simple cases, in low dimensions, we can use existing techniques from finite element and finite difference methods to know what the committer looks like. In general, the committer is either 1 or 0, close to the two metastable states, with a sharp change in the energy landscape in a part known as the transition region. In general, the committer Q satisfies the committer boundary value problem, and this was a discovery by Van den Einden and Wen and Il. And the goal of our work is to solve this boundary value problem. Now, one of the approaches pursued by our group is via diffusion maps, which is a nonlinear dimensionality reduction technique proposed in the 2000s. The main approach follows in this way, where we take the committer boundary value problem and discretize it using the diffusion map generator L epsilon. The main merit of this method is that it is suitable for dimensions higher than 3, where finite element and finite difference methods often are prohibitively expensive. The main drawback in this method, however, is that diffusion maps require sampling by this invariant density, which leaves the transition region under-resolved. As you saw earlier, most of the points sampled by the invariant density exist close to the metastable states A and B, which means that the accuracy of the committer we find in the transition region is going to be low. We can ameliorate this problem by using a technique called enhanced sampling, where you modify this density in a variety of ways to obtain points in different regions of the energy landscape. But now the question is, how do you go back and approximate the generator L? It turns out that we can use target measure diffusion maps as a fix to this problem, where we modify the diffusion map generator with a target measure diffusion map generator that allows us to sample the energy landscape by any choice of density rho, but then approximate the generator in the committer boundary value problem. This method we see works in practice, but theoretical guarantees of the accuracy of this method have previously been undeveloped, and this will be our contribution. As a brief summary, target measure diffusion maps proceeds as follows. First, you have data sampled with the sampling density rho. And using this data, we create a random walk on it using a Gaussian affinity kernel and a bandwidth epsilon. The role of this bandwidth epsilon is that it controls the affinity of each data point xi to all its neighbors xj. Smaller the epsilon, lower the affinity. We renormalize this random walk and introduce the effect of the target density mu. And the generator of this random walk, L epsilon mu, is the one that's supposed to approximate the commuter boundary value problem. Now, the main question is, how should we choose the sampling density rho and the kernel bandwidth epsilon? Some preliminary data suggests that there is indeed an optimal epsilon. We can choose an epsilon optimally to minimize the root mean squared error. But what this epsilon is unclear, and in general, this error model has been previously unexplained. The goal in our work is to give a quantitative description of this error behavior. So first, we summarize our approach. We take the continuous commuter boundary value problem and we approximate it with the target measure diffusion maps generator. And the mathematical question we will seek to address is, what is the rate of approximation of L epsilon mu to L in terms of the kernel bandwidth epsilon, the number of points n, and the sampling density rho. The approach we'll take is that we'll calculate this limit in a two-step process. First, we'll take the convergence of the discrete generator to the continuous one with respect to the number of points. This error in approximation is termed variance error, and it comes up because of the Monte Carlo approximation to integrals. And now we incur another error due to the fact that epsilon is positive, and as epsilon goes to 0, this generator converges to the generator from the commuter problem, and this error is termed the bias error. Putting this ansatz on the top, we summarize a few of the prior results from literature. On the bias error, the error with respect to epsilon, Banish, Terstanova, Klus, and Koltai in 2020 proved that the error decays at the rate of order of epsilon, but they did not discuss the convergence rate with respect to epsilon or the prefactor. The variance error, meanwhile, can be studied using a related technique given by Singer's theorem for Laplacian eigenmaps, which states that the variance error behaves according to this error model of square root of 1 over n and an inverse hyperbolic law with respect to epsilon. Now, our contributions involve elaborating the bias error by computing the prefactor on the order epsilon term, and obtaining the variance error by generalizing Singer's formula to the case of target measure diffusion maps. So first, we'll discuss the error with respect to epsilon, the bias error. And we have the following elaboration of the order epsilon, of the coefficient on the order epsilon term. We find that it depends on the fourth order derivatives of the function f and the sampling density mu, sampling density rho, and the target density mu. To compactify our notation, we've introduced these operators Q and R, which are fourth order differential operator. The main novelty of this error formula is that it describes the dependence of the error with respect to the sampling density, which was previously unknown in the first work on target measure diffusion maps. Now that we have the bias error formula, let's look at the variance error, the error with respect to n. We can prove a theorem with respect to the variance error in terms of a concentration inequality, where we have a precise formula for the standard deviation of the discrete generator with respect to the continuous generator. Using this concentration inequality, we can derive the following error model between for the Monte Carlo approximation error. As we see, the error model formula closely resembles the formula obtained by Singer in 2006, where the error with respect to epsilon follows this inverse hyperbolic law that depends on the dimension of the system and the number of points, 1 over the square root of n. But the prefactor on the convergence rate is now much more complicated. It depends on this function we define t and the target measure we choose mu. Using these formulas for the bias and variance error, we can obtain a very general error formula by putting the two estimates together. Now, it turns out that if you are solving the committer problem in particular, and rho is taken to be a constant locally, then we can cancel an entire term in the bias error formula, which results in the conclusion that we should uniformize our data set when solving the committer problem. Additionally, if the first derivatives of the function f are zero, or are close to zero, then we pick up an extra factor of square root of epsilon in the error formula, which enables us to alleviate the sensitivity to the choice of the kernel bandwidth parameter.
Shashank, please
Yes.
show various committer equations that gets zeroed out in this error term and explain how we can make rho constant.
So in this equation, we have the bias error formula. We can put it together and see that if the committer, so this is the committer equation part. If we do the algebra and figure out the expansion, then f actually eliminates this entire term. And if rho is constant, then Laplace rho is zero and Laplace rho is zero here. So this entire term is zero. And since it multiplies out on this epsilon over 16 factor, this whole term cancels out.
Mm-hmm. And we can post-process input data by converting them into quasi-spatially uniform set, so-called delta net. That's why we have very good control of the sampling density here.
Indeed. And with these things in mind, we'll look at some numerical results to conclude. To summarize, our error model looks as the follows. There's an inverse hyperbolic law with epsilon, and then a linear form that comes from the bias error. And as Dr. Cameron summarized, the technique we used for pre-processing our data set is delta nets, where we take a data set sampled by an enhanced sampling density, and we greedily delete points in a delta-sized ball around each point. This enables us to uniformize the data set and eliminate the sort of higher derivatives of the sampling density as we saw earlier. And to go back to the error figures that we get using this uniformization process and solving the committer problem, we see that that solving the committer problem with this sort of uniformization does reduce our error. And in fact, it even stabilizes the region of sensitivity in epsilon. The caveat here is obviously that this uniformization causes us to drop the number of points, which means that away from the sensitive region, the uniformization technique incurs a higher error. Another confirmation analysis that we can do is we can see model error curves corresponding to this error phenomenon. And we do see that dropping this exponential factor and reducing the coefficient d indeed drops the minimum error of this error curve and flattens out the region of stabilization of the kernel bandwidth epsilon. In this way, we've shown that in our example, the error behaves according to our model, and the error curves indeed show this sort of drop in error as you drop the prefactor on the epsilon and reduce the prefactor on the linear term. In conclusion, in our analysis, we computed the prefactor on the order epsilon term in the result by Barnish et al. And we generalized Singer's theorem to the case of target measure diffusion maps. And on the way, we discovered that our error depends on the higher density derivatives of the sampling density rho, and we can now eliminate these derivatives by making rho uniform. Additionally, when solving the commuter problem in particular, the commuter is mostly flat near the transition, near the metastable states, and this allows us to pick up an extra factor of epsilon to the half in the variance error that allows us to flatten the region of sensitivity around the optimal kernel bandwidth parameter. This suggests a simple pre-processing technique for our data sets by using DeltaNet, and we are undergoing future work on other strategies for reducing the error. With that, I thank you for your attention, and I'm happy to answer any questions.
Thank you very much. You can stop sharing screen.